So, just a couple things. Vectors can be graphed. Not all vectors, just good vectors. Okay, so I can take my XY graph here that you know, and let's say I have a vector which is 1, 4, and another vector which is 4, 2. And I want to add those together. Okay? What do I get? Well, I get a vector which is 5, 6, right? 1 plus 4 is 5. 1 plus 4 is 5. 4 plus 2 is 6, yes? Can I draw those on the graph? Well, the answer is yes, I can, because that's x and that's y, right? So I've got a point up here which is at 1 and 4. And I draw that line and I put a little arrow at the end of it. That little arrowhead tells me that that's a vector. And then the other one is 4, 2, which is right there. So that's 4, 2. That's 1, 4. That's a vector. Okay? And if I add those together, I get 5 and 6, which is out here. Okay? And I can do that. There's actually two ways I can do that. I can draw a dotted line from there to there. That dotted line is exactly this line. Okay? Or, he said, I can draw a dotted line from there to there with a little arrow on it. And that dotted line is exactly this arrow. So I can actually draw this arrow and then draw that arrow, right? I could take this arrow here and take this arrow and basically pick up down here and put that down there and then move that whole arrow up, and that gets me to that point. Yes? Are you seeing us getting to the moon now? Do you see what we're doing? Because our spaceship is headed this way, and then we do something to it which makes it is pointed this way. If I want to get here and I start this way, then I've got to go this way. It's beautiful. Yes? It's beautiful. So I can show vector arithmetic, if only in 2 dimensions here, but I can show vector arithmetic using my graph. It's beautiful. It's beautiful, right? That right there is that right there just moved over. Yes, yes. And if you say, well, that looks kind of like playing pool or something too, and yeah, it might be that too. Okie dokie. Some rules we need to know. Okay? Some rules we need to know. So, we have all these rules in math, right? We know in math, a plus b equals b plus c. We know that a times b equals b times a. Those are normal math rules, right? We learned, hopefully in school, we learned that things are commutative and distributive and associative. Well, matrices don't quite work the same way. So, rules in matrices, a plus b does in fact equal b plus c. So that's commutative. That one works. A times b, though, does not equal bc, or ba. It could. Do you like that? AB does not equal BA. It could, but only if B and A are the same matrix, for the most part. Okay? So this law still works. A plus B equals B plus C. And A minus B equals the opposite of B minus A, the negative of B minus A. That still works. But A times B matrix does not equal B times A. In fact, you might not have a B times A, right? If this is a 3 times 2 and this is a 2 times 4, Yeah, 2 times 4, 3 times 2. I can't even do that. I can't even find b times a. Okay? Are we good there? All right. We have the distributive rule. Which says a times b plus c equals a times b plus a times c. And that still works, strangely enough. That still works in the matrix world. It's the same rule that works in regular algebra, and it works in matrix world. Okay? In the regular world, we also have associative. Yes? And so if you have a plus b plus c, right, and you do those first and then you add c, that's equal to a plus b plus c. Okay? And that still works in the matrix world. It doesn't matter what order you add them up in if you're adding them all up. Multiplying might or may not work. In the real world, if you multiply a times b and then multiply the sum of that times c, in normal algebra, that works, right? 3 times 2 times 1, if I multiply those first, equals 3 multiplied times 2 pi 1. That works. In matrices, might is the best you can say. There's a chance that it works, but probably not. Odds are there's something, it might not work. Okay? And remember, the reason things work or don't work is because of dimensions and that kind of stuff, and we could have those problems. Okay. We already talked about what the identity matrix is. Let's remind ourselves. Identity matrices have to be square. An identity matrix has to be square. That means it's a 1 by 1, a 2 by 2, a 3 by 3, a 4 by 4, a 5 by 5. Okay? Has to be square. Square, 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 square. Okay? Square. It has to be square. Square, square. Okay. No? All right. Square. So an identity matrix is a matrix that has ones on the principal diagonal and zeros everywhere else, right? 1, 1, 1, 0, 0, 0, 0, 0, 0. Okay? Those are identity matrices. And identity matrices act as the number 1. In the matrix world, an identity matrix is the number 1. We also have what's called null matrices. And a null matrix is a matrix full of zeros. Okay? Null matrices act the way 0 acts. If I add this matrix right here, if I add that matrix to any other matrix, it's not going to change it, right? And adding 0 to 5 is still 5. Adding a whole bunch of zeros to a matrix still leaves that matrix. Multiplying 0 times 5 gives us 0. Multiplying the null matrix times another matrix gives us, 0. So the null matrix is the matrix equivalent of 0. Okay? A null matrix is the matrix equivalent of 0, and an identity matrix is the matrix equivalent of 1. And again, how are we going to do all this? We're going to practice. Practice, practice, practice. Now, couple of exciting things. Among all the many exciting things we need to do. Yes? So the first of these many exciting things is to learn to take a transpose. All right? And we identified transposes by a thingy. So let's say I have the vector 1, 2, and that's A. The transpose of A is A with a little, yeah, no. So you can think of it as an apostrophe or whatever you want to think of it as. It's a little mark that we stick up there, okay? And that's equal to the transpose, all right? It's a prime signal, right? So we could say A and A prime, though really we want to say A and A transpose. In a transpose, all we do is flip the rows and the columns. So the first row becomes the first column, the second row becomes the second column. So this becomes this way. This is a 2 by 1. It's going to become a 1 by 2. This is the first column. It becomes the first row. Is that easy? If that's A transpose would be 2, 3, and 4. Okay? Are we fun there? How about this one? How about 1, 2, 3, and 4 equals A? What's A transpose going to be? Well, the first column becomes the first row. So 1 and 3 goes from being the first column to being the first row, and 2 and 4 goes from being the second column to being the second row. Is that good? Is it helpful? Helpfully good? Let's try another one. Here's A. A is a 2 by 3. That means A prime, A transpose, is going to be a 3 by 2. The first row becomes the first column. The second row becomes the second column. And that's it. Is that hard? No, it's easy. Okay? Transpose means we flip the rows and the columns. We flip the rows and the columns. And you're saying, why would we ever do this? Well, let's suppose I want to multiply this matrix times something, but I want to multiply it times a 2 by 2. Well, maybe I can multiply the transpose, where I can't multiply the actual. I can multiply. You with me? Yeah. So there's stuff we're going to do with these transposes that are going to make our lives much more simple. Okay? Yes? Yes. Now, one other thing. A times A transpose, what do we know about that? If I multiply a matrix times its transpose, what do I know about it? Well, in this case, I'd be taking a 2 times 3 times a 3 times 3 by 2. Back here, it'd be a 2 by 1 by a 1 by 2. This would be a 3 by 1, 1 by 3. Has everybody got it? The answer is A transpose is always going to end up a square matrix. It turns out in life that there are things, and we're going to just do this in a second, is find this inverse. Remember? We want to figure out how to find this inverse. Well, it turns out that we can only find an inverse of a matrix that's square. If you're not square, you can't find your inverse. Well, so I can't always find the inverse of A, but if I multiply A and the transpose of A together, I can always find the inverse of that. Okay? And that turns out to be a helpful thing for us to know. Okay? And you notice that you can do it either way. You can find A transpose, and you can also find A transpose A. Is that exciting? Yeah, they're so cool little matrices, these transpose babies. Yeah? We be transposing. Because who wouldn't want to transpose? No? Yes. Okay. And it turns out that the sum of the matrix and its transpose, if they're square, right? If they're square to start with, if A is square. So if I have again, 2, 4, 5, 12, that's A. And I take the transpose of A, what do I get? Well, I get 2, right? The first row becomes the first column. The second row becomes the second column. Okay? Yeah? Yeah, yeah. Yeah, yeah. Okay? And if I have a matrix B, and B is 1, 4, 6, 2, the transpose of B would be 1, 6, right? 4, 2. Yeah. Yeah, 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 yeah. Okay. Add up A and B. I get 3, 8, 11, and 14. Yes? Add up A transpose and B transpose. I get 3, 11, 8, and 14. Oh. 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 Now you're like, whoa, that was so cool. Okay? Yes, these things are so cool, these matrix things. So